and I was doing for 4 years, mainly 3.5 years, nutrient mobilization from sewage sludge biochar, and how biochar will be useful if we apply some microorganisms there, and microorganisms will help to solubilize phosphorus, mainly phosphorus and other nutrients like potassium, calcium, magnesium, sulfur, these nutrients. So today I will present the phosphorus fractionation affected by autoclaving, and how this biochar, autoclaved biochar, will act in seed germination. Additionally, I will also present the effect of organic acids for nutrient solubilization from biochar. So you can see from the title that distribution of phosphorus fractions, biochar pH, and seed germination in sewage sludge biochar affected by autoclaving and incubation. Introduction, I will give the introduction. Who don't know what is sewage sludge, and sewage sludge is mainly generally the material after wastewater treatment. So it's the waste product after the water treatment. And what I will tell you about the advantage of this sewage sludge. So it's rich.
I hate to interrupt, but we don't see your slideshow. We're seeing your folders, all your folders, but not your slideshow.
Is it okay now?
No, I still only see your folders. It looks like you've highlighted bioenergy, but it didn't open on our view.
Yeah, now click on that. Yeah, it's opening, I think.
Is it okay?
No, not yet opened. Is it opened in your computer?
Yes, it's open in my.
Yeah, just a minute. Stop screen sharing and then start it again. Yeah. Now we can see another picture.
You can see now.
Yeah, we can see your screen now. Desktop. Yeah, now we can see the.
Now it's okay.
Yeah, now it's okay.
And you can see it full screen.
Yeah, full screen.
Okay. So I was telling about the advantage of this sewage sludge. So it's rich in phosphorus, nitrogen, micronutrients, organic matter, and it can help to soil fertilization. And disadvantage, there are many more disadvantages, like it's contain heavy metal, it's contain pathogen, organic pollutants, and everyone knows it's difficult to manage. So this next part is the new idea everyone knows about thermal processing, which is called pyrolysis. So we are pyrolyzing sewage sludge biochar, sewage sludge, and then we are getting sewage sludge biochar. These three disadvantages, like heavy metal, pathogens, organic pollutants, are remediating when we are processing the sewage sludge by thermal processing, I mean pyrolysis. So heavy metal is present, but it's it's becoming not plant available. So it's not plant available after when you are converting this waste sludge to biochar. And pathogens, of course, they will die in this high temperature. And organic pollutants, little bit it's present on biochar, but most of the part is not available to the plants. So most of the disadvantage we can reduce by converting it to biochar. And then I will tell this story at the last, this filament frost fungi and solubilization of phosphorus. So now we will go to the procedure. So feedstock. So feedstock here is the sewage sludge biochar I said, and pyrolysis temperature. We are preparing biochar in two high temperature, 520 degrees Celsius and 620 degrees Celsius. And then we are autoclaving, because when you are doing something with microorganisms, you have to do autoclave. So we divided the biochar into two parts. One is autoclaved biochar. Autoclaved biochar, you can see here is the autoclave machine, and then is the non-sterile, I mean non-autoclaved biochar. Then we incubate these two biochar 15 days. And then we tested pH, phosphorus fractionation, water extraction. And this, we extracted the biochar with water, and then we tested the seed germination with tomato seeds. I will tell everything in details. So next one is, this is the hypothesis. These three hypotheses we set. So autoclave, you can see it's written here. So we hypothesize that positive effect on the, so a positive effect will be in case of solubilization of phosphorus. Autoclave biochar has no toxic effect on seed germination, and citric acid is the most promising for nutrient extraction from biochar. And objective, you can see from here, identification of biochar, sterilization mechanism of action through biological and environmental friendly approach. We will discuss. I will show you everything in details. So now the next slide, I told you about here the phosphorus fractionation. We got the biochar after autoclaving and non-sterile. So here we tested phosphorus fractionation of the biochar. So we extracted first with water, and then 0.5 molar sodium NaHCO3, and then 0.1 molar NaOH, then HCl, then NaOH. What does it mean? Water extractable phosphorus generally shows the water soluble phosphorus which plant can easily take it. And this amount, 0.5 molar NaHCO3 extractable phosphorus from biochar, this is generally phosphorus which is associated with aluminum and iron oxides and hydroxides. So this part is a little bit also plant available, so plant can also take this part. But this NaOH extractable phosphorus, HCl extractable phosphorus, and NaOH extractable phosphorus are not plant available. So with this experiment, we are generally want to know what is the fractions that is plant available and what is the fraction that is not. So this is one method, one procedure for testing, and second one was the seed germination bioassay test. So seed germination bioassay test we did with tomato seeds, and we prepared water biochar extraction. Just we took 1 gram of biochar and 10 ml of water, and then we extracted, we set for 2 hours, and then 5 ml of the extract solution we applied for seed germination. And we made 3 concentration of this extract, 2.5%, 5%, and 10%. Here you can see how we measured the seed germination assay. After 5 days, we just took the seeds and we measured the length of shoot and root. I will show you the results. And now I am talking about these materials and methods. And now, after that, I will show. So this is the first one, phosphorus extraction. This is the second one, seed germination. And this is third one, biochar extraction by organic acids. So we took 12 organic acids, acetic acid, quinoic acid, and benzoic acid. As you can see from here, it's written, everything is written here. So these 12 organic acid we took, and then we took different biochar here. So we took also this 520 biochar, 620 biochar, and one of our PhD student also prepared this 220, 320, and 420 biochar. So we took also this biochar, and then we extracted with this organic acid solution. And then we measured different elements through ICP OES, potassium, mainly phosphorus, then potassium, calcium, magnesium, iron, and aluminium. So this was the method. And then I am coming to the results. If anyone has some question from this materials method, he can ask, or maybe at the last, whatever you want. So this is the results from this, sorry. This is the results from this fractionation, phosphorus fractionation, as you can see. Water soluble phosphorus, NaHCO3 extractable phosphorus, NaOH extractable phosphorus, and different other. And here is the sum of the extractable phosphorus. As I told you that water extractable phosphorus is plant available, and NaHCO3 extractable phosphorus also plant available. It's a little part. So you can see from here, non-sterile biochar, the water extractable phosphorus was high, significantly high. You can see the significance level here. I put BB, it means higher significance levels. So you can see the non-sterile biochar was higher in water extractable phosphorus. And here also non-sterile. And you can see also here non-sterile. So before incubation, after incubation. Here also the before incubation, after incubation. We incubate for 15 days. So before incubation, the non-sterile biochar, the phosphorus fractionation was high. So it means you don't have to incubate the biochar, and it should be non-sterile. You don't have to autoclave. Just to prepare the biochar, and you can apply to the soil or in the rhizosphere zone, whatever you want, and you can get higher amount of water soluble phosphorus. From these results, the conclusion comes that non-sterile biochar, here also non-sterile biochar. So it means for NaHCO3 extractable phosphorus, you don't have to sterile, but you can incubate or may not be. Both are more or less same. You can incubate or if you want, don't incubate. So the results is for these two treatment is the same. And the other things, I am not going to the details because it will take much time. And this is also not plant available, so we are not bothered about that. So next part, I am going for seed germination. So here is the results for seed germination. And here I presented shoot length and root length after germination. You can see from here, there was no significant difference with three different concentration. I told you 2.5%, 5%, and 10%. So these are three different concentrations. And this line is indicating the germination only in water. not with anything, no biochar extraction, nothing, only with water. So we can compare with this line. So you can see non-sterile biochar, high temperature, 620 degrees Celsius. Non-sterile biochar is more or less okay. I mean, it's recommended to apply non-sterile biochar, high temperature biochar. And also here, it's strange that we got sterile biochar for low temperature, 520. You cannot, it's not low temperature, but in here it's low temperature. So you can see for sterile biochar or low temperature biochar, you can see the higher shoot length, higher root length, higher root length, and you can see significantly high. It's significantly high from here. But it was contrasting with non-sterile biochar also for high temperature biochar. So the results are little more biochar. So we can conclude this result as this biochar dependent on the this feedstock. I mean, sewage sludge is dependent on temperature, and for sterile and non-sterile, it's completely different. There are many factors. We cannot tell what is the cause, what is the particular cause of this kind of effect. So it's strange result, but these findings can help in future research. So we will see. We will go to the next part. I mean, extraction with organic acids. Okay. As I told you here in the materials method, we extracted different biochars here: 220, 320, 420, 520, and 620 biochar with 12 different organic acids. So, and then we measured these nutrients: phosphorus, potassium, calcium, magnesium, and iron, aluminium with ICP-OES. Now I am going to these results. So here is the results for this extraction, and we hypothesized that citric acid is the best for nutrient mobilization for biochar. So we hypothesized citric acid because we also found citric acid is the best for nutrient mobilization from soil. So that's why we hypothesized citric acid will be also best for nutrient mobilization from biochar. We got also the same results. The citric acid is the highest. Citric acid is the most effective one for phosphorus extraction from biochar. So in future, it will be recommended to use citric acid for phosphorus extraction from biochar. So now I will show you the different nutrients we extracted by different acids. Here is all the results are combined here by principal component analysis. So you can see phosphorus is here. Phosphorus is coming out from here, and phosphorus is here. And these are different biochar. So you can see these different symbols: non-pyrolized control, 220 biochar, 320 biochar, 420, 520, and 620. So these are different steps, and red color means citric acid. So you can see citric acid extracted biochars, these biochars, the phosphorus content was high. So it's near to the phosphorus and iron. From here, we can get two results, like phosphorus extraction is higher, as I told you before. And we can see this iron also very high. So we can assume the phosphorus was in the biochar as a form of iron phosphate. And aluminium also here. So aluminium phosphate or iron phosphate in the sewage sludge. Calcium is very far from here, so it means calcium phosphate was not that much as comparison to iron and aluminium. So we can get this kind of result that aluminium phosphate and iron phosphate and aluminum phosphates was high in sewage sludge, and citric acid is the best one, as I told you. And the other acids you can see are clustered here. So these acids are not that much effective. And one most interesting thing is 620 biochar, 620 degrees Celsius biochar is here. So it was strange. It's far away from here, and it's near to the aluminium. So it means for when you are increasing temperature, the composition is changing. And what will be the future research plan for this from this experiment? So we are now doing an experiment with microorganisms. Here we applied citric acid as an acid, like a chemical. So now we got microorganisms which can produce citric acid. So our plan is to apply these microorganisms to biochar to get more phosphorus from biochar, bioavailable, and phosphorus from biochar by the effect of these microorganisms. So we don't have to put any citric acid in the biochar, and we will get like eco-friendly nutrients from biochar, high temperature biochar. Here also I have to mention one thing: this 320 degrees Celsius biochar was the best for nutrient extraction. As you can see, it was very high here. 320 bio, it's very upper side, and so it was very high. And non-pyrolyzed sewage sludge was also near to the phosphorus, but we are not telling about sewage sludge. We are discussing about biochar. So you have to this was control. So you have to focus on this biochar 220 to 620 Celsius biochar. So we are now found one microorganisms. Its name's Aspergillus niger. You can search on the internet that Aspergillus niger is very promising for producing citric acids. So we are culturing these microorganisms and we are applying in biochar. Then after the treatment of Aspergillus niger, we will apply this biochar to soil, and then we will get the results. Maybe in the next meeting, I will present you the results from these plant vegetation experiments. Now it's very preliminary. So now this is the conclusion. I already told you the conclusion that this experiment condition incubation microorganisms in future, it will be, if you want, you can read the conclusion. I already described the conclusion, everything. And thank you very much for your attention. And if you have any question, you can ask me.
Doug Iverson, and it's not really a question. It's something I learned long ago in the printing industry, that phosphates sublime. At high temperatures, they evaporate. And and it might be, yes, phosphates do. At high temperature, phosphates evaporate.
No, from my point of view, no. And I asked this question also to my professor, and he said no. It will not evaporate. It can bind and it can combine with other materials, and it will be non-bioavailable. But phosphate cannot evaporate. I am not agree with you for that.
Yeah, it would explain why your phosphorus levels are lower at the higher biochar temperatures. And yes, the reason I say phosphates evaporate, and I'm so certain of it, is in the printing industry, one of the best things to use in the fountain solutions were phosphates. And when the printing industry started using precious metal catalysts in the afterburners, they were being poisoned with phosphorus. And everyone's going, how are we getting phosphorus into the exhaust stream and poisoning our afterburner catalysts? And then that's when we discovered that phosphates evaporate as low of a temperature as 350 degrees Fahrenheit. They are evaporating.
350 degrees Fahrenheit. Okay. Okay. So as you were, so I will check that, and I will let you know. You are on LinkedIn, right? So I will tell you. Fahrenheit. Okay. And anyone else have any question?
Is there anyone having any questions on Chandra Sekhar Paul's presentation? So
Hi, this is Muthana here.
Yes,
Yeah.
And I have a quick question.
Yeah.
And if you go back to the slide where the germination, with the seeds germination slides.
Yes, yes, yes. Yes, here.
Not this one, the one with the charts.
This one.
Yes. And I have noticed here, even the non-sterile biochar at 620 degrees are the best performing. And I see here the 5% actually performed better than the 10%. Do you know why this has happened?
6 for root length?
Yes, if you look at the last brown column in each table, so figure A and figure B, the last brown column on the right hand side. So both of them are at 5% is higher. It looks like it's higher growth.
In 5% and 2.5% it's higher, and in 10% it's lower.
Yes, so that's the question. Was there any poisoning here or any? I mean, why? What's the reason?
We did not tested the toxicity assay of the biochar, so this will maybe the next research for new PhD students. So, but here you are right that in 10% it's decreasing, so significantly decreasing. So you can see it's C and BC, so it's significantly decreasing. So we made a report about that. What concentration will be most suitable. So if you want, I can send you the full report.
No, that's absolutely fine. It was just a remark here I've noticed.
Yeah, you are right that it's decreasing, and you can also see here non-sterile. It's higher in 2.5% and medium in 5% and lower in 10%.
Yes, but I don't know why is at 620 degrees it was doing much better than the others.
Yeah, 620 is.
I know in pyrolysis, with the higher you take the temperature, the more soot you produce, the more methane started to gas off, and biohydrogen started to come off, and carbon monoxide increases as well. But you know, that's more or less to do with, I think, around 700 degrees. That's when you started to get the nasty bits.
The purpose of using this high temperature biochar, 520 and 620 both are high temperature biochar. So biochar is a byproduct. So generally people use this pyrolysis mechanism for making oil and biogas. So high temperature biochar is most suitable for getting more oil and more gas. So we are planning to use this material. I mean, after this pyrolysis, after getting most of the oil and most of the gas, the byproduct is the biochar. So we are planning to use this part only. So that's why we tested only with 2 high temperature biochar, 520 and 620. So this is the reason, and you are right that it's everything. Some properties will change in high temperature biochar as content is high in high temperature biochar, and most of the nutrients are not available. So high temperature biochar people don't like for agricultural application, but as I said, for this oil and gas production purpose, we are using this high temperature biochar.
Thank you.
You are welcome. And anything else? Anyone else? Anyone else have any question? No.
Yeah. So can we move